So good afternoon, everybody, and thank you everybody for joining this talk today in the Sustainable Mobility Forum. Before we start, I will talk in the session about data and technology, and you will see that it's a quite critic view. I want to stress before we begin that I'm not against technology or data, so I'm in favor. But I want you to see that there are other things that also are important to achieve sustainable mobility. So I am Professor Francesc Soriguera. I am associate professor at the UPC in the Civil Engineering School, and I'm also member of the Barcelona Innovative Transportation Research Group. And now I'm also the coordinator of the Master in Urban Mobility. This is a master within the EIT Urban Mobility Framework, which involves several universities across Europe. And as you will see in the presentation, my research is mainly involved in traffic management with the presence of autonomous vehicles, which is a topic that we will cover a bit today. And I'm also working in vehicle sharing system. That is a topic that we will cover in a future session in this forum. So I have divided my presentation in 3 blocks. First, I will give general concepts about sustainable urban mobility, more or less to set the context, to identify the goals and the problems. Then we will move to a second block, which is about data. I will talk about the new trend in achieving more and more data, and if this alone is the solution or not. And in the third block, I will talk about the different technologies that are now arising as future solutions for urban mobility. And I will also highlight the potentialities or the problems of these technologies. So for this session, I thought, when I thought of this session, was more as a talk in a forum, and in a forum for a debate or discussion. But I have also included some learning goals that can be seen as goals from a lecture. So if I would need to highlight 3 learning goals from the session today, this is the first, to understand the sustainable mobility concepts. Second, I will talk a bit about the wardrobe principles of traffic assignment. So here is the concept of user equilibrium versus system optimal. And the third concept is about the car following implications in the lane capacity. And we will show a case for the case of autonomous vehicles. So this would be the 3 learning goals for today's session. So starting into the concept, so the first thing about urban mobility, the first thing that we need to ask ourselves is who wants to move? What's the demand for urban mobility in cities? So I tend to say that the potential demand for mobility, it's extremely large, at least extremely large with respect to the capacity of the infrastructures or the capacity of the urban spaces. So there's a lot of people and everybody wants to move. So we as a society, we need to move for work, to interact, to reach other opportunities. Some people thought that with the eruption of new communication technologies and the internet, so this would be the end of movement, because you can have almost everything in your homes. The result has been that in these completely connected cities, the movement is more important than ever before. So the communications, the electronic communications, has not implied a reduction in the requirements for mobility. So then if the demand is so large, the question should be why we don't move more. So the answer is because moving costs time and money. These are what's called the perceived cost of mobility. When you move, you need to invest time and money for moving. So this is why the demand for mobility, for urban mobility in cities and also countrywide, it's directly related to the wellness, to the economic status of the country or the city. The higher the resources, the higher the levels of mobility of any city. When there's an economical crisis, the first indicator is the reduction in mobility. So if we want to move in our cities, so what we really want, when we ask for transportation. So our desires are to travel where we want. This means that we want, if we need to express the mobility as a desire, we want door-to-door travel. So from your door of your home to the door of your destination. We want to travel whenever we want, so at any time, and we want to travel fast, safe, and cheap. And if it's possible, we want to travel with some comfort and with some privacy. So one of the transportation modes which fulfills all these conditions, or almost all these conditions, it's the private car. So the private car is a perfect example which satisfies our desires. So one would expect that the private car is the perfect solution for urban mobility. So what happens? What happens is that the car, the private transportation with a private vehicle, turns to be highly inefficient, but this is only true in high dense demand environments. So in cities, in the urban environment, when there's a lot of demand for mobility, this is where the car tour or the private transportation turns to be inefficient. Why this private transportation is inefficient in dense demand environments? So because the car requires one vehicle per person almost. So this means very large fleets. And these fleets are most of the time not used. So they are most of the time parked. This opens the door, as we will comment in some time, of sharing these vehicles. So the private vehicle, the car, implies a large space consumption. So it takes a lot of space, and then and in urban environments, the urban space is a very scarce resource. It's highly inefficient also because there's intersection of flows, and when there's an intersection, you need to regulate this intersection. You need to control the flows, and this implies a large reduction of the capacity of the streets or arterials. Then there's all this creates what's called the transportation externalities. So this creates congestion. This creates also pollution, so emissions, air emissions or noise emissions. It creates also accidents, and these are called transportation externalities because they are paid for by the whole society. So all the people in the cities pay for this, not only the people who are traveling. And at the end, all this reaches the user with an increased time or increased cost of movement. And at the end, we will return to this later, the human driving tends to be inefficient and selfish, which creates suboptimal solutions. So these are several reasons why the car, which could seem the best solution to fulfill our needs, is inefficient and it's not an option in urban environment. So there are other individual transportation alternatives, which could be a solution which could fulfill the previous requirements of individual transportation, which are non-motorized alternatives like bicycling or walking, or also these new or old personal mobility vehicles like motorbikes, scooters, small items which allow you to travel in cities in a private fashion. But all these alternatives, for one or another reason, may be not available to all the population. So there are different types of users, different segments of populations which may not be able to use these vehicle devices. So then the alternative for serving the transportation in a city is the collective transportation. The collective transportation implies an efficient space consumption because the demand is consolidated in larger vehicles which are shared. It implies smaller fleets. With respect to traffic, the flow management is much easier, and it implies economies of scale. Economies of scale means that with growing usage, with growing demands, the cost per trip, the cost per person traveling decreases. So this means that the collective transportation will be better and better as higher and higher is the demand in terms of unitary costs. Also, in contrast, the collective transportation implies some penalties. These penalties are that the demand needs to be consolidated. Needs to be consolidated in time when the vehicle reaches your stop. This means that it involves some weights that generally we don't want to wait, but we need that to consolidate the demand in time. And it involves some access to the access points, some walking or using another mode of transportation to reach the stop in order to consolidate the demand in space. Then to give accessibility through the city, the collective vehicle needs to stop, which means that there are stops and lost times, and it needs to be managed, which means that it will require some operative cost and maybe some additional infrastructure. For instance, the infrastructure is especially costly or relevant when the collective transportation is railway based. So in order to compensate these costs, the demand, when you implement collective transportation, it requires higher demand and obviously an efficient design and operation. Well, then what's sustainable mobility? I have talked a bit about many different concepts of mobility in cities, and sustainable mobility is reaching an equilibrium between all these concepts, which results in a minimum overall cost for everybody. In general, in dense urban environment, this would require a modal shift, so to move from the car to this collective transportation or individual transportation, non-motorized or personal mobility devices. In order to achieve this modal shift in cities, you will need some kind of penalty to the car. If you do nothing, the penalty to the car is the congestion. So then the congestion makes people in cars to pay with their time. And then at some point, they will shift to other options less congested. But this is a very bad alternative because the wasted time in congestions is lost. So it would be much better to penalize the car in some other way, for instance, economically with tolls, so that the tolls that you get from the cars, this is a penalty to the car, so less users will be using cars if there's cordon pricing in the cities. These tolls can be used to subsidize the penalties of collective transportation. So this is what's called cross subsidies. So you take the tolls, the revenues from the tolls to private transportation, and you invest in collective transportation. The objective will be to achieve a modal shift between car and other modes of transportation, where we reach a sustainable share within the city with lower costs. A part of that, you need to remember that the car is inefficient in dense urban environments. This means that if the environment is not dense, so if we're not in a city, if we are in an interurban travel, maybe the car is the best option. So trying to implement other transportation modes in regions where the demand is very low, the density of demand of very low, maybe it's not a good solution. It may be counterproductive and it will be very costly. In these non-dense areas, the car may be the best solution for transportation. Then what we need to ensure is that these people using the car in regions where the demand is not very intense, when they approach the city, when they approach the urban environment, they have the option to transfer easily to one of these other modes. So the intermodality, it's another of the required properties to achieve a sustainable urban mobility system. So this intermodality, it means creating efficient transfer hubs where you can park your vehicle and you can ride in a collective transportation system. So the park and ride network is an element of transition between the non-dense environments and urban environments. And I think that it's a very important element of a sustainable mobility environment. So with this, I end the first block of the presentation about sustainable mobility concepts, and I will enter the second block about data. So my perception today is that many people, or not only people, but administration, companies, everybody is seduced by data availability. We have much more data than we have never had before. And this data is much cheaper or easily obtained than before. So we have communication technologies. You can have a lot of data in your mobile phones or in your tablets. So everybody is investing in getting more and more data and more and more and more and more detailed data every day. Administration, I would say that the most large investments of administrations in transportation in the last years has been in developing technology to get more data. I'm not against of that, but before you get the data and you make these big investments, I think that it's necessary to ask ourselves why we need this data. So the why question. And the second question would be which kind of data we need and which level of detail. And the last one is what we're going to do with this data when we have it in our databases. So which data treatment where we are we going to use? And my feeling is that many times there is not a clear answer of these questions when you invest huge amounts of resources to getting the data. The objective is always more data and more detailed without knowing what we're going to do afterwards with this data. So another consequence of this more and more detailed data is that it requires more computational power to treat this data. And it's known, or at least is also my perception, that the more detailed data and the more computational power we have, the less attention we pay to the fundamental knowledge, to how we treat this data adequately, so that we get the results that we get from it. In the background material that I have provided for this session, I provide some examples that I will not go through it, but there are very paradigmatic examples that when you have a lot of data, maybe you lose the sense of units and you compare things of different units, which makes no sense. Or that you truncate the significant digits of the data so that the data that it's been so difficult to obtain in such detail at the end is meaningless, because you have, in the aggregation process, you have truncated them not adequately. This happens usually in traffic management centers when they take very detailed data from traffic, or that you use wrong formulas for the aggregating and averaging this data, or that you don't align spatially correctly or temporally correctly, so that the temporal averages or the spatial averages are wrong. So these are common examples that are currently being applied to this data that we have in much more detail than ever before. So my warning is, please answer before all the three questions, have a clear structure of how you're going to treat this data, make it compatible with our traditional knowledge of transportation engineering, and after, use this data for your purpose. And someone may say, okay, but data is information. And if we provide information, for instance, to users will be better informed to take the decisions in the urban network, and this decision will lead to a better mobility situation. So I will now present a counterexample of how this is not true, so that giving information to users not always leads to better mobility in a system as a whole. It's a concept that it's not new. This was formulated by a traffic engineer, John Wardrop, in the 1950s, who formulated a very famous network equilibrium principles. And the first one is the user equilibrium that I will explain in a minute. That happens when all the users have perfect information. That is what happens today, that almost all users in a road network have perfect information. So the user equilibrium will be reached much more directly than before. So let's take as an example for this counterintuitive result of the autonomous vehicles when they need to take route decisions, how vehicles will take the decisions to take one route or the other. Okay? So the route planning in autonomous vehicles defines what's called a traffic assignment problem. A traffic assignment problem means that we know the origin and the destination. This is what the user gives to the vehicle. I'm here and I want to go there. The origin and destination are given, but the vehicle needs to decide on which route to take. This is called traffic assignment. The autonomous vehicles, one of the consequences of autonomous vehicles is that they will be rather homogeneous in the criteria for selecting the routes, the best route for their trips. So for instance, in the traditional driving, the behavior of individuals may be differently because all drivers are different. They have different preferences, different socioeconomic backgrounds, different past experience, and they may value differently the different route options. In contrast, autonomous vehicles probably will have an objective assessment of the indicators of each route, maybe the travel time or the cost, including the potential tolls or whatever, and they will make an objective optimal decision. So all the autonomous vehicles which will be much more homogeneous in taking this decision. In the traditional driving, it happened before the appearance of the navigation devices in the vehicles that each individual had different information in their car, and they don't have perfect information about the route. So that this different information of drivers ended in different route selections. In autonomous vehicles, all the vehicles will have in real time the perfect knowledge of the state of the network. So the same information perfect to all the vehicles in the road. And finally, the route, I have already talked of that. The routing objective may be different for traditional driving. It will be very similar for all automated vehicles. This is precisely the context when John Wardrop defined the user equilibrium. And the user equilibrium is this concept. Everybody has the same information and same objective, which is minimize the travel cost in a selfish decision. And this is what they're going to do the autonomous vehicles. And this is what we drivers do. When we take a decision, we try to minimize our own cost without caring about the system. If we need to take a route, we will take the one which minimizes our travel time. We don't care what's happening to the other driver. We are selfish in these decisions. So our travel cost, when I say travel time, I mean travel cost in general, which is based off travel time, tolls, fares, fuel, etc. All this will enter into the decision making of the autonomous vehicle. So in this situation, what Wardrop proved is that the network will reach what's called the user equilibrium. The user equilibrium will be that all the routes that will be used will have exactly the same travel time. And those that are not used will have higher costs. Otherwise, they will be used. And no user can change the behavior of the network by changing his unilaterally his behavior. So if he switches route, it will find travel times that are higher. So he will return the next day to the same route. What Wardrop proved also is that this situation, this selfish situation, where each vehicle is in his route, the one which is minimum cost for him, means that in a system-wide perspective, the solution is not optimal. So this means that there are other solutions which can result in better aggregate costs for the system. So here I have one example that I will not go into detail, but you have the material, so you can compute it by your own. It's not difficult to make the calculations. I will give only the results of an example of this user equilibrium versus system optimal situation. Okay, imagine that we have this setting where we have a freeway, where vehicles that demand QAC use this freeway to reach the CBD, the center of the city, by car. And here we have another demand, QBC, where there's other vehicles coming from urban development, that they have two options to reach the city. They can take the on-ramp and use the freeway to reach the CBD, or they can take some arterials, which will be slower, but at the end they will reach also the CBD too. So the route selection at this point is what defines the traffic assignment. So how many vehicles will go this way to the freeway? How many vehicles will take the arterial? As we said, if there's perfect information, these QBC users, this demand, have perfect information of the times here in the freeway and the times here in the arterial. So what they will do, they will take the freeway and the arterial so that the travel times in the both options are the same. When the travel times are the same, the situation has reached the user equilibrium. So this is the objective, to determine how many vehicles will go that way, how many vehicles will go that way, so that the travel times on both are the same. And this would be the route equilibrium. Obviously, you need the travel time functions as a function of the demand. So here you have the travel time. I have represented the network as a graph, and you have the travel time functions as a function of the flow on each link. So you also have the QAC and QBC in numbers, in vehicles per period. So you can solve these equations just implying conservation of flows and nodes and equilibrium of travel times in the network. And then you will get the flows that get into each of the options. So you will get the flow 1, flow 2, flow 3. I leave the exercise for you and I give you the result. I will solve it graphically, which is very direct, so that you will see the result. So if you plot the travel time in option 1 and the travel time in option 2, so the cross points, so I have used linear formulas. So if you see before, these functions for the travel time are linear, because then the computations are simpler. In reality, they are not linear, but in this way, the computations are simpler. So you have this linear representation of the travel times, and at the equilibrium point, it means the intersection of these two straight lines. It's this equilibrium point. This will happen, and at the travel time, this number is not stated here, it's 95 units of time. And for a flow which is 85 vehicles per period, or this can be 85 thousands or hundreds or whatever through the freeway, and 5 through the arterial. Okay, so this means that 85 vehicles will go that way, and 5 that way. This means that if QBC was 10, 5 would go through the freeway and 5 would go through the arterial. And with this traffic assignment, the travel times on both options would be the same, and would be 95 units of time. So this is the user equilibrium. Then if you compute the total aggregated travel time of all the users in the network, you only need to multiply the flows times the time. So for the user equilibrium, you have the flow 1 times 1, so this is 85 times 95, plus the flow 2, 5 times the time 2, which is the same, 95. So this means that the total aggregated travel time in the network is 8,550 vehicles per period. Okay, so this is the situation that we reach in a situation where everybody takes their selfish decisions. So take the decisions that minimize my own travel time. Just now imagine that we are a transportation entity, and we decide to close the on-ramp. So we decide to close the link 3. What happens if we close the link 3? It happens that all the traffic needs to go through the link 2. So this means that here the 10 vehicles from B to the city center will use the link 2. And here it will remain with the 80 vehicles coming from the freeway. So what's then the total aggregated travel time in this new situation? So like preventing vehicles from using the link 3. So it will be the same, the flow times the time in the link. So now the flow in link 1, it's 80, and the travel time in link 1, it's 90. If we sum with the flow of 2, which now is 10, plus the travel time here. Obviously, the travel time here is higher because you have put more travel time here, which is 100. But if you make the total aggregated time in the network now, it's 8,220. So you see that we save travel time, so we reach a better situation if we actually close one of the links, if we prevent vehicles from using this link. But this will not happen if we allow vehicles by their own to take the decisions. Why it will not happen? Because the vehicles that are in 2, they take a time of 100. While if they take the freeway, they will experience a time of 90 or at the worst of 95. So these vehicles, if we do nothing, the vehicles from B will tend to use on a fraction the freeway. But this means that a few vehicles coming from B will penalize a lot of vehicles coming from A. So it means that few vehicles penalize a lot of people by the selfish behavior of these few people. So control to reach this system optimal situation means penalizing a few vehicles for the benefit of the whole system, for the benefit of whole society. So the conclusion of this is that even in the future, when we have maybe 100% of autonomous vehicles taking perfectly optimal decisions, so using a computer program to optimize travel times, but traveling on their own, even with perfect information, but taking their own decisions at the vehicular level, we will reach a situation that it's not better than the one that we have today. So what's needed, it's a control option, which is not at the vehicular level, but at a higher level, at the infrastructure administration level, that controls the network and controls the decision taking by these vehicles, so that we can move from these selfish decisions to an optimal, a system-wide optimal situation. Until we don't apply this coordination, these traffic management principles, so this penalizing some to benefit the whole, we will not reach a better situation than the one that we are today. So this is the conclusion of this concept of data means information. Okay, not sorry, data means information, but information by itself, it does not mean a better system management. You can see that simply by looking what's outside the streets today. In the last 20 years, the traffic information has grown enormously, from nothing to almost perfect. What's been the effect in the efficiency of the traffic system of this information? My answer would be none. So we have better information, but we have the same congestions as ever before, and we cannot take better decisions than before. So this information, as I said, I'm not against of this information, but this information should be used by not only by the users, but also by the agencies and operators to apply these control strategies and to manage the system in order to move from the user equilibrium to the system optimal, in order to penalize or restrict a few to benefit many, to apply control actions, to apply enforcement. Okay, so this means taking action. Today, we have the information, but the traffic or transportation administrations have taken very little action. They are afraid of implementing transportation strategies which imply effective limitations to users, to population, because they think that it's unpopular. So there are many options in all the fields of transportation. For instance, in traffic, we can apply metering strategies. We can apply lane changing management. We can apply dynamic speed limit. We can apply dynamic high occupancy lanes. We can apply tolls. We can apply parking restrictions. So there are many alternatives, which are traditional alternatives of traffic management, with the help of the information that we have today could be applied very efficiently. But we need the compromise or the implication of the administration in taking action, in moving forward to implement these strategies. Also in collective transportation, We can prevent the vehicle pairing. I cannot enter into each of the problems, but just by Googling these concepts, you will find the problem. We can implement efficient ticketing. We can reduce lost times at the station. We can coordinate transfer. We can give signal priority to collective transportation vehicles. All this can be done better with communications and data, but it needs to be done. Data by itself will not give this efficient management. And also the last one is vehicle sharing. With all this data with demand, we know the origins with destinations, we can implement vehicle sharing initiatives so that the balancing of the vehicles across the streets would be optimal. We can eliminate or reduce the zones which are empty or full of shared vehicles. We can implement smart pricing. So there's a lot of potential of using this data, but as I said, all of them are related to system management and taking action, not only disseminating the information. Finally, for those of you who are working in transportation analysis, or you will do maybe a master thesis or maybe after a PhD thesis, and this will involve modeling some aspects of transportation, I also have detected in my past experience that there's a growing interest in microscopic modeling. So this means modeling the transportation system to the very detailed entity. So for instance, if we're modeling traffic, to take one car as the modeling entity, or modeling pedestrians, we take one human as the unit, not in aggregated terms. So we are racing, I would say, to models which are more data, which requires more and more data. So this can be, in some cases, positive. So the level of detail of the output will be larger, but you always need to have in mind that more detail means also more errors in the inputs, and more detail means generally more parameters, and it means more calibration. And the more parameters and the more calibration that the model requires, this is against the number, the robustness of the model. So the more parameters, the more calibration, the less robust is the model. The more uncertain will be the results. So I would say that also the transportation or the behavior of the individual entities in transportation in order to model the behavior of a single car or the behavior of a single pedestrian is kind of unpredictable. So we are transportation as a whole, on average, follows very direct physical rules. So the average flows are quite predictable. We as a society do more or less everybody the same. We go to have lunch at the same hour. So the peak hours in a city is quite predictable. All days happen the peak hour at the same hour. But if you want to predict when one individual is going to have lunch, this is much more difficult. So there's many individuals, there's a large variance. So it will be difficult to predict at the individual level which decisions this individual will take. So remember always, the sentence was set in a research paper many years ago by Professor Carlos de Ganso in UC Berkeley, that increasing the model precision sometimes can reduce the accuracy of results. It was in a different context, but I think that the sentence is applicable to the microscopic modeling. Remember always, I'm not against that, so it can be used, but remember always that you have alternatives. You have macroscopic modeling, and at least you need to compare the results of a micro model to the macroscopic equivalent. So we can model the traffic in a city with what's called a macroscopic fundamental diagram, that simply knowing the accumulation of vehicles in the city, then you can predict the flow rate, so the output, the rate of finished trips, and the average speed. And this can lead to very easily implemented control systems. So just restricting the inflow of traffic in a city. So it's like just governing how many vehicles go in because you know how many vehicles go out. A similar model was developed in the 50s and it's the well-known LWR model for traffic. So macroscopic models exist. They are extremely robust, very few parameters. So this macroscopic fundamental diagram, it can be assimilated to a triangle. So with only 3 parameters, you can calibrate how it behaves the traffic in a city, and it can lead to very easily implemented control system. So whenever you face a modeling objective, the first step should be to analyze which kind of model is best suited for your results, and not to think that always more detail will be better. So this would be the conclusion of this part of transportation modeling. So the conclusion of the data section, I would say that fundamental knowledge comes first and then data comes next. Data helps, but it's not enough. And not always more detailed data is better. So today, there's a lot of attractiveness and incentive to implement the latest technologies and to obtain a lot of data, but to my belief, the governance is missing. So there's a fear to apply transportation engineering principles and to move towards sustainable mobility. The fear is mainly based on the administration, on the policymakers, because I think that the society already, it may face an initial opposition, but after a few months, maybe, when realizing the benefits of the solutions, they will applaud the principles of urban mobility. So let's move to the last block, the third block of the presentation, which is about technology. This will be shorter. So transportation has always moved in pair with technological development. So it appeared the railway as a result of the steam engine. It appeared the car, the automobile, as a result of the improvements in mass production in the US. So now there's other initiatives, other technological developments that many people feel that this will be a new revolution in urban mobility. I have named a few, and I will comment briefly a few. So the autonomous vehicles, the electric vehicles, the flying cars, the hyperloops, the teleportation. So are these possible, or are these the solution for the urban mobility problems? So let's try to get an idea of what are the pros. I would say the pros, if you look at the news, you will see the pros. Everybody seems to be in favor of this technological evolution. But I will concentrate in what are the difficulties that these systems will face. So I read constantly and since many years that the autonomous vehicles will be the solution of traffic congestion. So self-driving cars will ease traffic congestion. Is this true? Is this true? So everybody says that the autonomous vehicle will reduce congestion, but nobody says how. So I will try to illustrate a bit on this question. So I must say that the vehicle, the research on autonomous vehicle is mainly vehicle-centric. So this means that it's based on the technology in the vehicle, and this favors comfort and safety. This means that the parameters that are used for the development of these cars are pretty conservative. And I will illustrate what I mean. Here you have the basics of car following theory, how two vehicles follow each other. So this is what's called a time-space diagram. In the vertical axis, you have a space, x, and on the horizontal axis, you have time, t. And here you can see the trajectories of two vehicles. The slope of these trajectories are the speeds. You have a vehicle n, which is the leader, n plus 1 is the follower. So you can see that the follower follows the leader at a given gap. So this is the space in between. And this gap, considering the speed, the derivative of the space with respect to time, it gives you what's called h, which is the headway. The headway is the time between the passage of two consecutive vehicles. Okay? The headway is very related to the flow. So the flow that goes through one lane of vehicles following one each other is the inverse of the average headway. You have here the formula. The flow Q, it's equal to the inverse of the average headway. Like the density K is equal to the inverse of the average spacing, but we will not enter this. Just keep this in mind, that the flow is equal to the inverse of the average headway. The capacity of one lane is defined as the maximum flow. So the capacity of one lane will increase as the average headway is reduced. Okay? So let's see what happens. Let's see what happens with when we have autonomous vehicles in one lane. So this is a very simplistic analysis. So here on the horizontal axis, you have different magnitudes for the time gap, this time headway between vehicles from 0.8 seconds to 2 seconds. Okay. And here on the vertical axis, you have the flow that travels on that lane, depending on these time gaps. And you have different colors. So the different colors are the different penetration rates of ACC systems, which can be seen as autonomous vehicles in the car following scenario. So you can see, for instance, that for a time gap of 1.1 second, for all the penetration level, the capacity is more or less the same, around 2,500 vehicles per hour. Okay, this is because the time gap that human drivers live is around this magnitude, around 1 second, 1 second 10. So then if we have autonomous vehicles which travel at the similar gaps, so the flow will not be affected, so the maximum flow will not be affected by the penetration rate of autonomous vehicles. If autonomous vehicles use time gaps which are below 1 second, then you see that the higher the penetration rate of autonomous vehicles, the higher the flow that can be achieved. So if you achieve a time headway of time gap of 0.8 seconds, you can achieve more than 3,500 vehicles per hour here. Okay. On the contrary, if the time gap that autonomous vehicles live, it's larger than 1 second, so 120 up to 2 seconds, the higher the number, the penetration of autonomous vehicles in one lane, the lower the capacity of the lane. Can you guess what's the average time gap used in the design of current autonomous vehicles? So I'll provide the answer. It's around 1.6 seconds. So between this and this, almost 2 seconds. So this means that the parameters used in the design of the car following of autonomous vehicles are more conservative than the ones that we use as human driving. So this means that if we implement to higher penetration rates autonomous vehicles on our freeways, the congestion would be not lower than today, but much higher, because the capacity of the lanes will be reduced on almost 500 vehicles per hour. Okay, so this means that there's no reason to think that autonomous vehicles can be the solution for congestion. On the contrary, if we do nothing, it can increase traffic congestion. I will explain this in a minute, but the potential lies in coordination. If vehicles are coordinated, we can reduce these time gaps, not 2.8 seconds, but because of the communication between the vehicles and the coordination, we can reduce lower than 0.1 seconds. And then you can increase significant capacity increase in one lane. This is what's called road trains or platooning of autonomous vehicles. Well, so this is what I have commented, that the autonomous vehicles can be detrimental if treated as selfish vehicle decisions, but if we coordinate them, they can improve traffic significantly. So traffic management, so this coordination entity which will coordinate the traffic of different autonomous vehicles with the ability of communicating between them will be much more necessary today. The good news is that will be easier because you will be able to communicate easily with the vehicle actuators. So if vehicles are autonomous, you can make them to steer, you can make them to select routes, you can make them to adapt to a new speed. You don't rely on the behavior of the drivers. So the autonomous vehicles will be the traffic actuators. So this means that if we implement traffic management, the results will be better than today. So I'm running a bit short of time, but just a few more ideas and we end. About the electrical vehicles. The electrical vehicles I'm extremely in favor, and they will probably substitute the combustion engine vehicles in the short period. And this will have a very positive impact in the reduction of the pollution emissions locally in the cities, which is very welcome because this is an important problem in many cities, which is related to health issues to the citizens. However, in terms of mobility, not talking in terms of health and emissions, in terms of mobility, I would say that it will create some additional problems because the batteries are expensive, are of limited duration, are unsafe. So there are some underground parkings that are forbidding the parking of electrical vehicles because of the risk of firing, are difficult to recycle, require charging stations, which need to substitute the current pump stations. It creates a range anxiety to the users, so that you need generally at your origin, at sometimes at your destination, this point of charge for charging your vehicle, because otherwise you are anxious about running out of battery. And most important of all this will be solved with time, and technology will evolve, and this will be and people will adapt, and all this that I have commented will be solved in the short medium term. But what it will not be solved is that an electric vehicle is still a vehicle. It's still a car, and the mobility problems, congestion problems are exactly the same as before. So there's no benefit in changing from one combustion engine car to an electrical car in terms of traffic flow performance or congestion mitigation. So these are two pictures, life without electric cars and life with electric cars. So congestion is exactly the same. What about the flying car? The flying car, it's not a new concept. This appeared in magazines in the 1950s already. Also in the 1920s, in some fairs, in some industrial fairs appeared kind of prototypes or ideas for future mobility. So it's more than 100 years old, and every month or every year we have new pilots in different countries from new startups that they say that they have in operation the flying car. So my concerns about this is that this type of transportation is very sensitive to weight and weather. The battery power is limited, so they will face restrictions with respect to the energy and range of the trips. The price is prohibitive, so the cheapest of these vehicles is 1 million euros. They will require pilot licenses. There will be air traffic regulations. You will need infrastructure for taking off, for landing. So this means that this kind of transportation will have all the problems of traditional cars and many others. So I don't believe that this will be a general transportation alternative that will solve the urban mobility in the future. It may be used as an helicopter travel from one point to the other for a few people, a few rich people probably, but not more than that. This is my guess about the flying car. What about the urban hyperloop? There's been also what's an hyperloop? It's a pipeline travel. This is how in the 1960s it was defined in a comic which is called the Jetsons. It was the pipeline travel. There's pipelines and people travel inside vehicles, small vehicles, very fast by magnetic levitation to different parts of the city at prohibitive speeds. This involves many small stations underground. There's been pilots, or they are building pilots in several places in the world. There's a debate if technologically this is feasible. So it seems to be extremely unsafe, extremely expensive, and maybe not making the vacuum into these hyperloops will consume a lot of energy. It will require a lot of material for these tubes to be resistant to the pressures. So it's not clear if this is technically feasible. But even if it is, even if it was, this is not more than a subway with small vehicles and very high speeds. But what's the problem here? The problem in urban mobility is that the commercial speed is not sensitive to the maximum technological speed. It's not the maximum speed which gives you the door-to-door speed in a urban environment. It's the it needs to make stops because people need accessibility to different parts of the city. And at every stop, you will lose time. You will need stops, you will lose time. And at the stops, you will need to transfer. And this will also lose time. So the maximum speed is not an important issue. It's more important to design correctly the stops and the transfers. And I've not seen how this is going to be done. So I don't understand how we can provide city coverage and accessibility to the whole city with hyperloops, and how people will transfer from one hyperloop to the other. So this could be a solution, or if it's technically feasible, a solution for some interurban travel, or maybe for sending small parcels in a city for urban logistics, for some high value parcels to be distributed through the city, but not for human transportation in cities. This is my feeling. And the last one, it's about teleportation. There's been experiments. So this is kind of a Star Trek vision of moving from one place to the other by just disappearing and appearing. So there's, surprisingly, I'm not a physicist and I have no idea of how this works, but surprisingly, there's some experiments. But it seems that these are called quantum teleportation. It seems that what happens is that you change the state of the matter in one place, and this information is instantaneously transmitted and it changed in another matter in other place. But it's not the matter which physically changed from one place to the other. So I would say if it's information which is transmitted, not the objective itself, how this is compatible with human mobility in cities, I don't think that we will see the Star Trek teleportation in the near future either. So I have presented different options for technology in urban mobility, some that are present. So from data management, traffic management, autonomous vehicles, electrical vehicles, sharing systems, some others that will appear in the future, flying cars, hyperloop, teleportation, which, as I said, I'm not very optimistic about them. But what I want to stress is that even if all this technology is feasible, we cannot avoid applying the principles of transportation or traffic engineering if we want to achieve some results in a more sustainable urban environment. So with this, I end my lecture. Sorry, I'm a bit late, but I hope that you've got at least the learning outcomes that I promised at the beginning. So thank you very much for your attention. And if you have some questions, there's a few minutes, I think.